Hello everyone, this is Gary Marr from Glendale Community College. This screen capture is for my SAS 150 AB online class. And in this screen capture I'm going to discuss concepts and terms and technologies discussed in section 4 of the textbook. This particular section is all about modularization or procedural programming. In section 2 we talked about identifiers and expressions. In section 3 we talked about structures which gave our programs intelligence and decision making and some oomph. And what we're going to do in this particular section is we're going to help you decide and determine how to break your complex program into pieces so that they're easier to understand, they're more reusable, and they're of higher quality. So this process is called modularization, and it's done in all programming languages, although the name modularization and module is kind of a generic term, whereas languages like Python and Java and the C family of languages will call these small units of code functions. Visual Basic will be procedures and subroutines, and then as we get into class objects, functions become methods. These modules are small blocks of code. They are part of the bigger application. So for example, in its simplest form, I might take an application and break it down into modules of input, processing, and output. If it's a bigger application, let's say I'm developing a cash register program for Walmart, I might have one module that has sales input, one module that has sales discount, one module that has loyalty program, one module that has taxation, and etc. Breaking these complex problems into pieces or blocks of code, so when all the code blocks are added together, is very common in programming for a whole host of reasons, of which we will talk about in this next slide. One of the things that's really important about this class in object-oriented programming is understanding the benefits of code reuse. Application programming is labor-intensive. It takes a lot of time, and it's real easy for people to start to reinvent the wheel, so to speak. So if I'm calculating, let's say, an algorithm that converts euros into dollars, I might have one version of that logic. Somebody else might have another version, and it might be a third version. Whereas it'd be much smarter and more efficient use of time, and probably a higher quality solution, if we took the best solution and we all shared it. So when we create modules, what we're basically doing is saying that this block of code here, let's say it's sales tax calculation, is one that is going to work all of the time for this company in a consistent fashion of high quality. And just because somebody else developed it doesn't mean I should not use it also, and therefore cut some time off my application development. It's going to be higher quality, it's going to be quicker to implement, and time is money, so that's a good thing. The other thing that you get from modularization is you get the ability to work in a team. The team could be across the company's location, it could be across cities. But given the complexity of technology today, I might have someone working on the cyber technology part of my program. I could have another person working on the database. I might be working on the application that's running on the internet. Another person could be working on the application that runs in Linux. We all need to be able to work together. And if we break this code up into modules, we can all focus on our piece and then combine the pieces together at the end for a better solution. The other thing that happens here is when you do modularization, you basically take a complex problem and break it down into pieces. Go back to my simple example where in my application, if I created modules for input, processing, and output, it would be easier to understand than if I didn't have anything at all. If I just simply put some statements in one file and one block of code, that's not as easy as if I break those code statements down by their general purpose in the application: inputs, processing, output. Dividing or breaking up the pieces is very important in terms of taking complex problems and making them easier to understand and have them be a higher quality solution. This screenshot here is a visual, it's an image. This just kind of shows you what is happening in terms of how this code is being called out. I mean, maybe the simplest way to think of this is a little bit like working with a web page. That link you click on takes you to a different page with additional information. And then when you hit the back button, you return back to the code or back to the original page to continue your reading. That same kind of thing is happening here. We're going to create a lot of little blocks of code that are going to be strung together for the bigger solution, but it's going to be of higher quality, it's going to be more reusable, and better for our organization. I mean, just think in the case of sales tax calculation. I mean, if this was Walmart, how many different people are going to write applications that do sales tax calculation? Well, it could be the customer service county, it could be a cash register, it could be the person who's doing the store reports. Why should we all come up with our own algorithm, our own logic for calculating sales tax? Why not use one for all of them? That way, if there's a problem, we fix it once and they're all fixed. Or if it changes, we change it in one spot and it replicates to all the places that need it. It just makes sense. This is fundamental to modularization, but it's also fundamental to object-oriented programming too. In flowcharts, what happens with modules is that we change the symbol. So when a module is called, okay, the symbol is a rectangle with lines down the outside or lines across the bottom. Visio does lines down the side. What that is, it's a signal to the flowchart reader to go to another section on the flowchart which would have that module and all of its statements identified. So I believe this is the logic for that module, and this module would be over here. I don't think we do too much with flowcharts and modularization, but that's how you would reflect it in a flowchart. Better way to look at these things from here on in, as the code gets more complex, it's a lot easier and simpler, I think, to look at pseudocode. So here's a pseudocode example of that same problem. We've got our main application or our main program here, and it's calling out calc discount and calc sales tax, which could be module used by a whole host of other applications, but our application also uses them. So what happens? It comes down here, executes this logic. This is all pseudocode at this point. Here's a call statement. Now, I typically use call for my pseudocode. You can use invoke or whatever you want to use as long as it's consistent to indicate that there's something out there, a module that I want to execute. Now, typically you want to show the parentheses because that's the clue that it's a block of code or a subtask of this bigger application. You're going to find in a minute or two when I talk about some other slides, these parentheses can also carry with it inputs that are passed to the module, but in this case it simply calls the module, executes these two statements, on the return comes back to the call point, goes to the next statement. Now that's the end of the true branch, so the next statement would be down here, which is another call. It's going to run this block, and then finally comes back to print total cost. So again, you can use the analogy of the internet and a link. That's one way of looking at this. And the object here is this. As you become programmers, you're going to be using a lot of people's code. If you're developing applications, and let's say in HTML even, you're going to use the input element to capture input into a text box. Behind the scenes, somebody has created a whole bunch of code which is going to draw that box on the screen. It's going to accept the keyboard input, reflect it inside that box, and then allow you to store it someplace to use later. Sometimes you're reusing other people's code and it just doesn't seem like that's possible at all. I mean, when we use Windows or when we use a browser, we're using other people's code, and it's considered to be of high quality. And the other thing that happens here, and this is critical with understanding code reuse and also class programming or object-oriented programming, is that when we start calling out modules, we're actually practicing what's called abstraction. When they had such a big backlog of programming back in the 60s and 70s, they looked at other technologies that would allow them to create applications quicker. Well, they knew that if they could reuse code, it would cut the time of application development, but they also looked at how humans process data. We process data based on messages. So in other words, an example I like to use is overhead projectors in a classroom. I ask my students, do you know what the plastic, how to make the plastic, that case on the overhead projector sits in? Do you know what the schematic is for the board that actually creates the image on the screen? Do you know how the power management system works inside that data projector? Well, they don't. Most humans understand typically what the inputs are, know that it's going to process something of which they don't know the details of, and that they expect to get some output which was described to them as being part of that thing, in this case being the data projector. So most people, when they put a data projector in front, if you put a data projector in front of them, will understand it has to be plugged in. Yes, there's a wire there, and it looks like it goes into the receptacle. It has to be turned on. It has a focus and a volume. And then it has to be plugged into your computer. How it works outside of that, they have no clue. And this is how we're able to tackle so many devices. And this is what makes the human brain so much more advanced than a computer, because the computer has to be told everything. And so one way to make it easier for us to talk to computers is to break things down into modules. And you're going to find that as you program, you're going to have a lot of modules available to you, where you'll have the input, you'll know what the inputs are, you won't know how it does it, but you know what it's going to give you in return. And this has really pushed programming logic a long ways down the road, and it allows us to begin to accept or catch up to some of the demands placed on us by organizations to develop new technology and to fix technology that's broken. I guess that's my speech for the day. Modules. This is a little thing here, just a question thing that would you kind of should run yourself through, is in terms of what makes sense for a module. I mean, you don't have to use modules. You can write everything line after line and don't break it up into pieces or anything. If it's a complicated program, you could have 10,000 lines of code without one module. It would be a nightmare for anybody else to try to look at and change, but you could do this. What are some of the things you want to consider? And that's what this slide will talk to. Usually with modules, what we have also, if there's a lot of them, is we have hierarchy charts that we'll develop for people who are looking at our logic. And what this does is that identifies that there's a main program, of which we've had in previous slides here, and then it'll have all of the modules that are called by the main program identified. And if one of those modules calls another module, identify that. And this becomes like a top-level context diagram that helps you navigate around the code that's part of this application, and outlines what modules are used. And just like when you name identifiers, you want the names to be relevant and informative. Well, you're hopefully going to pick module names that will give the reader some kind of idea as to what that module will do. Once they have this, they can then take and figure out how it's called, and if they want to also, they can open the code and look at it. The other thing that comes into play now that wasn't a problem in the past is Identifier Scope, local and global. Basically, when you start using variables and constants and modules together, you have a modifier that will help you lay out your code. Two modifiers. One's global and one's local. If the modifier is global, then the identifier is available to any line of code in the main program or any of its modules. It's kind of like a wild card. If it's a local modifier, that would mean that the identifier is only available within that function itself or within that module itself. Most people would probably say, then why not make everything global? Because that way, if I forget something, it's available and I can just use it. Because that's just kind of an easy, sloppy way of doing it, but it is sloppy. The reason you want to separate local and global variables is if the variable is truly used by all of the code and all the modules, maybe it's accumulating test scores or something like that, yes, you would want to make that global. But if a variable that you're setting up is only used within that particular module, then make it local to that module. The reason you want to do this is if you try to reuse that code now, let's say that you've got, I'll go back to the cash register. Let's say you've created a module for Walmart on returns. If you make sure that all of the variables and all the constants within that module are local, the person will be able to easily use that code block within the application they're creating, which might be for something totally different, but it does have a need to calculate that same logic that you had in yours, or use that same logic you had in yours. If it's local variables, they can pick it up and drop it in there. If it's global, or if it's got global variables as part of it, then what can happen is they can pick the local variable up, they may not see it, may not understand it, they'll forget the global, they'll add it later on. Now you've got a global, they've got a global. It kind of gets out of kilter. The reusability is now compromised, and the likelihood for an error has been increased. So you want to try to make that distinction if possible, and that'll be hit again when we get to classes. What makes modules a little tricky is these next two slides. it's possible to send, and this has got to do with local and global also, it's possible to send data from your main program or from one module to another module. And the way you send it is through an input parameter. So you would use in the call statement the name of the module, then any one or more pieces of information you wanted to pass to the module. Now the module would have to be written in a way so that it was able to accept those pieces, and each one of those pieces would have to have its own separate identifier name. But once that happens, this information is now local to this particular module, can be used by that module to do whatever it needs to do. In this case, it's going to calculate sales tax. So here's an example of input parameters. They could be one, there could be many, but the call point has to have the number of parameters that match the number of parameters that you've identified in your module. The second part of this is you can also return data from a module. Instead of having a return statement by itself, you can return a variable or identifier that's inside the module. So this one, for example, has one input parameter, and then it returns a calculated value at the end of the process. The easiest way to usually see that's coming is that if it's a module that doesn't return anything, it typically is the module name and any input parameters. If you see an identifier equals, or if you see that as input to something else, there's a pretty good chance this must have a return, and it's going to return something back to the call point to be used at that call point. In this case, it's going to return back a value to be stored in total cost. What makes this complicated is now there's a whole bunch of variability here. I can have a module that has no input parameters and no output coming back out. That's called a void function or void module. I can have a module that accepts no or some input and returns a value. That's called a fruitful module because it's returning something back. And there's a whole bunch of combinations there. Obviously, I can have input parameters and a void, no input parameters and a void, and the same thing with the fruitful functions. So that takes some practice, and there will be some practice as part of this assignment or part of this section. I'll have some more videos for you guys and some more examples to look at. You'll probably also start to see more Python now, because one of the nice things about Python is I can show you how this works in pseudocode, but the real proof to the pudding is running it, because that way we know it all executed correctly. Pseudocode is okay, but Python's really where the rubber meets the road. That will, with values anyways, be able to tell you whether you're on target or not. So you'll start to see more of that now. Module parts. This will be on the test. There's a header, there's body, and there's a return statement with optional parameters. So the header consists of the name of the module and the parameter list. And again, this is also called function and methods in other programming languages. The body is the statements and return again. If it's a void function, it doesn't return anything. If it's a fruitful function, it returns a value. And that's what these two things here are telling us. This particular example down here, there's the header, there's the body, there's the return. This is a fruitful function with an input parameter. And again, you can have all kinds of variation here. One of the things that will happen as you get into languages, especially like Java, there's an extensive libraries of reusable code. And typically what they'll do there is they will tell you, okay, if you want to use this particular code, maybe creates a PDF file. We need to have as inputs the name of the file and where you want it to go. So it's got two inputs. It'll tell you essentially what it does, creates a PDF file. Won't tell you how it does it, but it'll tell you what the return is. Now the return could be a return code, 0 if it's good, any number of error codes if it's not. Maybe it returns the file name. But it'll lay out in the application programming interface or the API the rules for using that module. So if I was to go back, the API for my overhead projector was, I have to plug it in, I have to turn it on. It does some processing, and the output should be an image on the screen. That information is critical for code reuse. It's critical for object-oriented programming, and this is the first chapter that we're exposed to it. If you have any questions, don't hesitate to ask. There should be some examples out there in this module for you to look at also. Thank you.